Okay, so this week, and at least the next, this week, and the next two lectures next week are going to cover vibrations. So the plan right now is I'm going to skip a little bit in terms of section order because it makes a little bit more sense to talk about rigid bodies and free vibrations and then move on to damped free vibration. We will do damped free vibration, we will do force vibration, and I will probably do damped force vibrations relatively quickly because I like it and I think it's worth doing. The last lecture, I haven't decided what to do yet. We'll still talk about that later. But today, everything is similar to the lecture we had last Thursday. And of course, the big difference is that rigid bodies rotate and translate. And so as you're looking at these problems, you've got to think about, well, often moments make more sense than forces. And as I said last week, particularly in this text, you need to follow sort of a cookbook approach. You want to set up the equations so they look a certain way. All of the terms, mx double dot plus kx, has to always be mx double dot plus kx. If you end up with minus kx, your solution will not work. Again, we're not doing a lot in terms of analysis. We're just taking the free body diagram and working from there. Unsurprisingly, you're going to deal with a lot of springs. And with springs, you kind of, at this point, what we're seeing is solutions that never dampen out. Guess what will happen probably next lecture, or even this lecture, we might start talking about damping. But what will happen at this point is that it will all be relative to a point of zero equilibrium, or the static equilibrium. And you always want to displace things and some forces or moments in positive directions. Ultimately, write your equations in the standard form. I've looked at other approaches. There are other approaches to do this, and they're quite clever. But the problem with it is that it does require you to keep track of the static equilibrium, set up everything in a certain way, but then you actually do analysis. So this chapter is a little bit weird, but you're still going to do quite a bit of work there. All right, here we have the first rigid body problem. So 1/3 L to the pin, 2/3 L to the end. There's the spring, and it's over here. Now I know G is at the halfway mark. So that's going to be 1/6 L. I think that's everything. Okay. And if I take a look at this, I have, I'm going to define this as 0.0. I'm going to define this as 0.0. Actually, I won't go there. OY, OX, MG, and P. So before I start this problem, I'm going to start looking at the static equilibrium case. So I have the pins, or the pin at 0.0, which is where that is. I have the center of mass, and I have weight acting downwards, and I have compressed the spring. So I compress the spring, the force is acting upwards. So the intrinsic force in the spring at the point of static equilibrium, I do a set of moments just like you did with your fond memories of Civ 100 at 0.0. So moment about from P, moment from the weight, and combining those you get mg over 4.
Is it mg times 1/6 L or L over 2?
L over 6, thank you. Oh, that's interesting. So I want to know, so what I've done, I haven't solved the problem, I haven't done anything yet towards the vibration. All I want to know is where's the zero position for this system. So I have allowed this thing to come down, and I have a P associated with it. But at this point, nothing's happening. So I've just taken that rod and gently allowed it to come down to 0. And by allowing it to come down to 0, I then have a static equilibrium, which is force of P equals mg4. Now again, I'm going to do the same thing, but now I'm going to look at the case where I have motion. And so I have the free body diagram here. I have displaced this downward. I put everything about 0.0. I have the force from the spring up, and I have the weight down. And so it'll be Oops. The last thing I should do. So here I have sort of the same sort of standard x, y coordinate system. So I have mg times L over 6 minus k times x plus delta static equals I naught theta double dot. Now, as I did in the previous lecture, everything is written in the double dot format. So for sum of forces in the x direction, I had sum of forces equals mass times mass times x double dot. For moments, I'm going to write them not as I naught alpha as I've done for all of chapter 6. Instead, what I'll do is I'm going to write them as I naught theta double dot because I want to write things in an equation form. So the end result of that is that I can get rid of those two terms from my expression because those are static equilibrium. I just solved in the previous part that under static equilibrium those terms don't play a role, and so the only thing vibrating is kx and theta double dot, which is not quite what I want here. So I know x is at the end of the rod. The rod is 2/3 L. That's my radius. And I can rewrite this as I naught theta double dot plus k times 2L over 3 times sine of theta, which does, yeah, it equals 0. And all of that is equal to 0. So this is looking a little bit better because I have everything in terms of theta. I've just done a switch for the displacement in terms of the arc length. And I'm kind of making an assumption here that this is not a big displacement, and that's one of the big things that you have to assume in all of these problems. And what that does is allow me to take this term, sine theta, and convert it to theta. Now, I really like I hate calculators, but I think one of the only disadvantages from my terms as an undergraduate is that you don't have tables of values. So this is not necessarily an intuitive sort of thing to do. But this sine theta to theta conversion actually works pretty well up to about theta of around 15 to 20 degrees. So if you're bored, plot the two, plot sine theta versus theta in radians. And you can convince yourself, and that's something fun to do with Wolfram alpha, by the way. So now I have this equation, which looks exactly like the equation I had last week. I have theta double dot plus k over I naught times 2L over 3 theta is equal to 0. This mess of terms is my omega n squared, which is my natural circular frequency. So I have, once I write that equation, I can solve through for all of the same terms and all of the same expressions I had in the last lecture, which might be worthwhile sort of reminding you of. Ugh. So you had in the last lecture these definitions, and all I'm trying to do in this particular case is write everything in the form square root k over m, or square root of the term in front of this single, well, the theta term here. So if I want it in front of the x, I put it in front of the x. If I want it in front of theta, I put it in front of theta. But that gives me my natural circular frequency. All of the rest of the things appear because of that. No. And if you want to do, well, I mean, and that's it. So all of these governing equations, all of these terms that you're looking at, it's important to sort of remember that we're only working with definition here. There are kind of different approaches to it, but it's not going to sort of do what you think it's going to do. The other thing that's kind of important, again, you'll notice that when I did the displacement here, I displaced, let's do this. I displaced it like this. Now, part of that is to have the static equilibrium because I expect it. I mean, it's easier with rigid bodies. But I cannot displace this rigid body up. Because one, I wouldn't be able to get rid of my static equilibrium term. And two, again, just sort of reminding you where we started in this particular lecture, take moments in the direction of positive rotation. Don't mess around with clockwise and counterclockwise. Counterclockwise, as far as you're concerned, is now written in stone. And it's really important that as you do the summation of these terms, that you look very carefully at how the displacement occurs so you write the equations correctly.
In this case, because we canceled out the static friction, then the theta would be the angular difference from the equilibrium position that's already displaced from her to the horizontal.
So in this case, my zero position,
It's not horizontal.
yes. So it's not here. It's going to be down here.
And the theta would be the difference between that and any new position.
And then the rotation or the vibration occurs here. So this is how you're setting up your equations.
So if this problem was like mirror and the spring was on the other side, would you then want to lift? Or,
No. Then in that case, I do it the other way around.
okay.
So I'd still cheat. There you go. There's always an exception to all of this.
If we assume that the position's like that, can we go back to the moment equation? Wouldn't the moment caused by P around O, wouldn't you have to use sine or cos? Because that's perpendicular.
For this particular case or another case? What
For
is?
the case where it's resting.
So the case where it's going up. So you can do it so that you reference everything to this position. But normally what you expect is that a rod will go down because of static equilibrium. And what you want is the spring displacement. And so that's your theta, that's your displacement in the spring, and that's why you're looking at sine theta. And the weird part of all of this is, as far as you're concerned, and as far as I'm concerned, this distance and this distance are the same. It's very, very small displacements.
Sorry, I just meant like, when we have MO at the top of the screen right there.
Yeah.
This is negative P2 over 3L. Wouldn't we have to use sine or cos for that? Because in the case that it's resting down, it's not perpendicular to the body.
Okay, and so that's, again, it goes back to this point that we are cheating.
Oh,
Okay, so the rod is like this, we let it go down, but we pretend this and this are actually the same.
okay.
So the displacements are never going to be, this is kind of a problematic chapter because you've got to make a lot of assumptions. but they don't really affect too much, and we're not meant to sort of we're just trying to get a first cut. This is probably the best way to refer to this as a first order solution. It is not the ideal way to solve these problems in most cases, or in reality. All right. So one of the things, again, just to remind you, you have to write them in the standard form. Everything with this solution, everything with or the way we're going at this, we are writing the equations, assuming a certain form, and we're sort of assuming things will sort of happen in a particular way. So, did I give myself, no. So you're asked to find the natural circular frequency of a pendulum, and the pendulum has a length L, it's got theta, and it has a mass. And again, as is usual in these cases, you have x, y in a positive moment that is counterclockwise. So maybe I should just leave the problem a little bit. So again, even though you're going to do something that looks a little bit different, you still are trying to write this in the same form. That is, you have sum of forces in one direction, you solve all for them, then you write everything in terms of theta. This is a particle problem, so it tends to be. But you have sum of forces tangential equals mass times acceleration tangential. And in this particular case, again, as you've done before with all sorts of pendulum problems, you can neglect in the tangential direction the tension. The tension disappears. So all you have is minus mg sine of theta, which is equal to ml theta double dot. Now, again, in this particular case, I'm assuming very, very small vibrations. And so I'm assuming this is going like this, theta, and my x can correspond to an L theta double dot. But it's, again, I'm assuming very, very small vibrations. This is not the case where you're sort of bouncing up and down or throwing a beach ball in the air. But as you continue through it, you can just get rid of those. You again write the same form of the equation. And you'll notice again that I made sure that my term there was negative. When it sets up the equation, this is positive, and I make the substitution for sine theta to theta. So all of that is really important when setting them up because you're not really changing how you're setting up the recipe. The terms end up being theta equals g over L square rooted, tau equals 2 pi square root of L over g. Your oscillation is going to be this if you use that form of the equation. And if you remember, that's one of the two forms of the equation that you had for a pendulum. Go ahead.
Are we assuming like the ball is going up, that's why the tangential direction is up, or?
Oh, we're just assuming that there's a part of this. So we have the weight acting here, and you have theta acting in this direction. So it's a negative theta.
But if you had assumed the tangential direction down, would that have?
If you had oh no, you can't assume the tangential direction down, right?
I mean like to this.
So if I had displaced the spring or the pendulum to the other side,
No, I mean to
Yeah.
this side, but I'm assuming that like the pendulum is going down, so it's directed this way. Yes.
oh, I'm not worried about the direction of the velocity, right? I'm only worried about the acceleration. I'm solving for the acceleration here. So if I solve for the acceleration, it also makes sense. Because my theta double dot, which is my sort of displacement, is negative. So it is accelerating in the negative direction. Now, it may still have a positive velocity because, say, for example, in the previous part of the problem, I displaced at negative 10 theta, whatever it is. And then you have energy, so you're going to have the pendulum swing through. But it's going to be decelerating as it moves through the arc. And so the velocity, I don't know. Because I don't know the initial conditions, I didn't solve for the initial conditions. But again, this is one of those problems where once you set up everything and everything sort of goes through, it's okay. But writing the problem and writing the form of the expression so that you have everything at the end is really important. Yeah, I think I'm going to start there. Now, one of the weird things about this chapter so far there we go, is that you see all of the solutions sort of as sine waves, sines and cosines, they're all adding up. But there's never any diminishment in time. So as time increases, these things continue to sort of go, and they still sort of operate no matter what. But I can introduce to my mass spring system a damper. And the damper will have a coefficient, which I'll just term c, but it's a function of velocity. It's not a function of acceleration like mass, and it's not a function of displacement like springs. And what I want to do with this is take care of the fact that as I look at my current solutions, they never sort of decrease in amplitude. So they continue all the way through. So what I want to do is introduce something that starts to bring down that vibration. So as I bring it down, how do I solve for that? So I'm going to introduce a dash pot. So C, the viscous damping coefficient, as units of Newton seconds per meter or pound force seconds per foot. So if I look at that same system as I have before, I have Kx. Actually, I'm just going to draw these in first, and then I'll change the colors. So I have Kx, Cx dot, normal, and there we go, mg. And in this particular case, again, I don't need to worry because these are particles about rotation, but I'm going to define my positive x in that direction. So I've defined a positive x. I have only added one term, but it messes up my solution. And the problem is that if I take the derivative of x like I did with mass, then I'm going to have an additional term that appears, and an additional sine and cosine, and it's not going to cancel out. So I need to look at how I'm doing my solutions. So sum of forces in x, mx double dot. I have minus kx minus cx dot, which equals mx double dot. And I end up with the same form of the solution as I've had before, which is mx double dot plus kx, but I also have this additional term that is going to appear, which is cx dot. And so my a plus a sine, or a cos omega nt plus sine omega nt doesn't work because it's not going to cancel out all the terms. And so if I can't cancel out all the terms, then I end up in kind of a jam here. So I need to sort of rewrite this. And I'm going to write it, ooh, that got away. X double dot, okay, no problem. X dot plus x is equal to 0. Here I'm going to write 2 zeta omega nx and omega n squared. So omega n squared is exactly the same term as I've had before, so that's okay, I'm fine with that. But the zeta term is new. And zeta is equal to c over 2m omega n. And I'm going to need that to sort of define how my damping is going. And I'm going to use this as a coefficient of damping that describes what's happening to this system. In addition, I need to sort of figure out a solution for this. So my previous solution was great because it canceled out, sines are canceled out, but this is not going to work as well. So I'm going to use a form of the solution that looks as x equal to a, which is still some sort of arbitrary term, e lambda t. All right, so I have that. I have those two terms there. Everything that I need. Let's see how this looks. So if I have this, I can write this as lambda squared plus twice squiggly zeta omega n lambda plus omega n squared is equal to 0. And what will happen is that all of the e lambda, the exponential terms sort of cancel out. So this is good. I have an extra term that appears, but I have lambda and lambda squared, and I have omega n, so this is all workable at this point, and it's a solution that is a quadratic, with the only addition of that bit in green. And if you solve for the roots of that, you end up with lambda 1 is equal to omega n minus zeta plus square root of zeta squared minus 1. Lambda 2 is equal to omega n minus zeta minus square root zeta squared minus 1. Oh, plus minus, okay, good. So you now have two solutions, and you have two roots, which doesn't sound like it's much better, but you have two lambda roots. So my solution, is going to look, x is equal to a e lambda 1t plus a2 e lambda 2t. So both of those kind of work. I have a solution. I can stuff it back into my equation. Everything is fine. So the mess of terms, and I always regret writing this, a1e to the minus zeta plus zeta squared minus 1 omega nt plus a2 e to the minus zeta squared minus 1 omega nt. Okay, so you have that, and that's your form of the equation. If you look in the text in section 8.2, you will see the same sort of development. So all of these solutions, this is also something that as you're looking at your crib sheet, spend the time to sort of put them in. You will see in the crib sheet right now, I think in all three of them, these forms of the solutions. Now the solutions may be slightly different. Oh shoot, yeah, they're going to be different because I think they're all from Hibbeler. But zeta will appear, but they use zeta a little bit differently than we do in Merriam and Craig. So we will continue with this. Oh, here. Oh, I think I'm going to be in trouble with this. Okay. So I have three cases. And I'm going to try and sort of work with three cases without three cases. Ew. Case 1. Overdamped. Lambda, or zeta, excuse me. Zeta is greater than 1. So your roots are all positive, and you have overdamping. Roots are real, distinct, and negative. And the motion decays to zero displacement. It's actually sort of asymptotically approaches zero displacement over a very long time. There is no oscillation. Okay, so that's all right. Critically damped is the second case. I'm going well on this one. It's going to go all the way to, but the nice thing is that when I do OneNote later, I can edit it and reorder it. So there you go. So case 2 is critically damp, but this is the case where lambda 1, lambda 2 are real, equal, and negative. Lambda 1 equals lambda 2 equals minus omega n. Now because, did I write the solution? So the form of the solution was, for the first case, is this, but for this form of the solution, it is x equals to a1 plus a2t e to the minus omega nt. So for this particular case, it's not just going to be, I mean, there's no point in putting two of the same solutions in there because you end up with the same result. So here, now, two things happen in this for these cases. One, the motion is decaying to 0 over a long time and is non-periodic. So both of the curves kind of look similar in that respect. However, when you do critically damping, then it reaches equilibrium faster than the overdamped case. So the reason why I was spending so much time to try and avoid that was to plot this. And I think this is from this text. It may not be. I have to check. But one of the things that is counterintuitive with all of this is that for the overdamped case, you have put in a higher value of the critical or the damping coefficient. Here it's 15 versus 6. And the sixth case actually reaches 0 or towards equilibrium and doesn't really reach 0 because you can tell from the solution they can't equal 0. But they approach sort of a minimum value or a sort of minimal, close to 0 value, much faster in the critically damped case than in the overdamped case. So you have to think about that as you're solving all of these problems. But the important quantity in all of this, the one that tells you what to do, is zeta. So if zeta is equal to 1, you have critical damping. If you have zeta equal to 2.5, you have overdamping. Where it gets a little bit messy is case 3. So this is for a case there, and I'm pretty sure it's from the text, so I have to just check. And the last case is underdamped. So lambda 1 and lambda 2 are both distinct and imaginary. What that does is change the form of your solution to a nightmare. So x is equal to a1 e to the 1 minus zeta squared omega nt plus a2e square root 1 minus zeta squared omega nt times e to the minus zeta omega nt. And the bit I have to add here is the imaginary bit. So I end up with an exponential solution, but it's an exponential to the power I. And what I'm going to do is I'm going to define that term right here as omega d, which equals omega n times square root omega n 1 minus zeta squared. So zeta is less than 1, by the way. So I end up with a damping coefficient, a damped natural frequency, damped natural circular frequency. Now, the one thing that I know that is useful here, and I keep having to shove over, is that e to the plus or minus ix is equal to cos of x plus I sine of x. And there we go. So if you're looking at cos x plus I sine x, then that kind of looks a little bit more interesting as a way of writing out these solutions. And I just want to write that as a sign. So your solution ends up being x equals a1 cos of omega dt plus I sine of omega dt plus a2 times cos of omega dt minus I sine of omega dt times e to the minus squig, this zeta, zeta omega nt. Okay. You can do a little bit of funny business here, and you can say A3 equals A1 plus A2, and A4 equals to I times A1 minus A2. And you end up at the end of this with a nice set of equations that kind of skip over all the worst bits, and you end up with A3 cos omega dt plus A4 sine omega dt times the quantity e to the minus zeta omega nt. And if you're bored, you can rewrite this as e to the minus c zeta omega nt sine of omega dt plus another phase length. Both of these are the equivalent solutions. They're just rewritten for the same cases. Just a second. Actually, go ahead.
What is omega d?
Omega d is that damped natural frequency which I just defined. Where is it? Right here. And rewriting it, just give me 2 seconds to get through this one because I do want to write these. Two things. Damped natural frequency. Again, sort of to respond to that last question, omega n, 1 minus zeta squared to the 1/2. Damped, period, tau d equals 2 pi